Another classical exercise is you are given scenarios and you must say the shape or graph that each one will most likely have. Distribution of salaries in a company. You probably know that in a company or institution, most people have moderate salaries and a few CEOs or directive persons make tons of money. So most individuals are in the left and few create a tail in the right. This is right skewed, something like this. Distribution of results when you roll a die 600 times. If we roll a regular die 600 times, how many ones will we get? Approximately 100. How many twos? Approximately 100. How many threes? Approximately 100, etc. This is uniform. Distribution of weights at birth for 3,000 babies. Babies weigh very similar when they are born. There will be an average. Some will be above the average, some will be below. The more overweighted, the less common, and the more underweighted, the less common too. So this is going to look like a bell shape. Distribution of life expectancies in 250 countries around the world. In most countries, the life expectancy is similar, between 70 and 80 years old. But in some countries, due to poverty, wars, or other reasons, the life expectancy is smaller, 65, 60, 55, or even less. So this is very likely left skewed. Distribution of heights in a sample of 2,000 randomly selected adults. This is like the scenario of the babies, but with adults. The point is that with adults, the two genders are very different. There is an average for men and an average for women. Men will follow a bell shape around their mean, and so will women around the woman's mean. So this is going to be multimodal. Exercise 3. The question is simple. Which of the following distributions shows greater variability? This or this? Assume that the variable represented is the same and the scales of the axis are also the same. I like this question because it's very simple and most people answer wrong. Most people answer A. Indeed, we have much less variability in A. Because the concept of variability refers the variable of interest. Let's see this with an example. We work with the variable age. This is 10 years old and this is 80. This is 10 years old and this is 80. In distribution A, most individuals are between 35 and 65 years old. There are some older than 65 or younger than 35, but very few. There aren't almost teenagers nor very old people. In distribution B, we have many teenagers, many people in their 30s, many people that are middle age, many elders. This means more variability. The average of both distributions could be the same because both distributions are symmetrical, so the average will be in the middle. But in distribution A, individuals tend to be closer to the average, while in distribution B, many more individuals are far from the average. This brings the concept of standard deviation, which we will study in the next chapter. Exercise 4. Here we have three distributions, each one with its median marked. You must mark the place where approximately the mean will fall. What we practice here is a key concept. In the next chapter, we will see that the mean and the median are the two most used measures of center, and we will work with them more intensively. The concept that we introduce here is that the median is more resistant. We say that a measure is resistant when it is not easily alienated by extreme values. we say that the median is more resistant, or stable if you prefer, than the mean, because it is not so influenced as the mean by extreme values, outliers, or tails. In the case of this graph, we see that it is right skewed. If the median is here, the mean will be more to the right, because the mean is more influenced by this tail and these outliers. So it will be sufficient if you mark the mean approximately here. The mean will be greater than the median. This second distribution is left skewed. If the median is here, the mean will be to the left, more sided with this tail, approximately here. The mean will be less than the median. This distribution is fairly symmetric. In a symmetric distribution, the mean and the median are the same and both fall in the symmetry axis. Thus, this would be a right answer. What we will see in the next chapter is that when the distribution is deeply skewed or it has great outliers, we prefer to use the median rather than the mean, because the median is more stable, more resistant to outliers and tails. Exercise 5. When talking about graphs, it's very common that books dedicate a title to how to misrepresent information with graphs or how to deceive with graphs. In fact, there could be a title like that almost in every chapter in statistics. You can mislead by picking a biased sample or providing the average without complementing it with measures of variation, or speaking of associations as if they were causations. All the awareness and good practices that we are teaching here, you can use them all the way around. We don't want that. The idea is that neither you mislead nor let others mislead you. Maybe books pay more attention to graphs because they are more commonly used in the media, so you are more exposed to them. In this exercise, we have two examples reportedly published by Fox News and CNN. Explain why each graph misrepresents information. In the graph in the left, we have a pie chart. The first stranger thing is that when we add the three pieces together, we get more than 100%. So how shall we understand this? What occurs to me is that maybe participants were allowed to support more than one candidate. This is weird in itself, but also, if this is the case, a pie chart is not the way to go. A bar diagram would be better. Because in a pie, if you eat one slide, no one else can eat any part of it. In other words, the slides are expected to be mutually exclusive. Finally, notice that with the use of the volume and the perspective, this piece that represents 60% may look larger than this piece that represents 70%. Working with perspective, whatever you put in the foreground looks greater compared to the background. So the general idea is volumes and perspectives are not good for graphs. Here you see the same percentages represented with a Pareto chart. This is clearer. What's the problem with this graph in the right? Here, this column looks 3 times as big as any of the other two. But if you look at the small numbers, this is 62, and each of the others is 54. So it's only 15% bigger, when it looks 200% bigger. What happens here is that they have cut the bottom part of the y-axis. This is not a good practice. Here we have the same Pareto chart with the whole y-axis visible. Here you can see that the differences between parties are not huge. In other words, what the original graph does is, in visual terms, exaggerating the level of descent between parties. Notice that this disproportional representation can be exacerbated as much as we want by cutting the y-axis higher. Now this column looks 3 times as big as this one. If we cut the y-axis here, at the level of the 52, this column is now 5 times as big as this. If we cut here at the level of the 53, this column is now 9 times as big as this. Because where to cut is totally arbitrary, the FAIR criteria is not cutting at all. These are just two real examples. I am sure that sometimes things like this are produced by human error or naiveness. But sometimes they might also be done on bad faith to manipulate the audience. Part of the benefit of a course like this is that it trains you on how to navigate the world of information that you live in.